Welcome back to a new video about analog filters. In this example we will discuss the Sallen-Key filter configuration. We will see how we can derive the transfer function for specific configurations like the 2-pole and the 3-pole configurations. And we will see how we can also determine the cutoff frequency for these specific circuits. Of course, we will see everything step by step in our calculations and verify these in SPICE simulations. Okay, let's now first discuss the outline. This video I spent actually quite a lot of time to prepare, and I hope this is going to help you understand the Sallen-Key filter configurations. First we'll discuss the Sallen-Key filter circuits, so that's for part 1. We will look at the 2-pole filter circuits. We'll be doing the low-pass and high-pass circuits. We will also look at the 3-pole circuits, again low-pass and high-pass. We will also look at the unity-gain configuration and non-unity-gain configuration, so we will have some gain, let's say 20 times or 10 times. The transfer function will be discussed in great detail and about how we derive the cutoff frequency, very important parameter in the filters. In part 2 we will go through many examples. You see here in this case 6 examples. We will look at the Sallen-Key 2-pole low-pass filter, Sallen-Key high-pass filter, again 2-pole. And then again, a similar situation but then for a 3-pole configuration. All of these 4 examples will be about the unity-gain configuration. And the final 2, example number 5 and 6, we will discuss the 2-pole low-pass filter and the 2-pole high-pass filter where we have a non-unity-gain. Okay, let's now go to part 1 about the Sallen-Key filter circuits. In this case we will discuss the 2-pole filter circuits first, and we will discuss also only the unity-gain configuration. First we start with the low-pass filter configuration. We see here 2 RC low-pass filters, R1 and a C1, that's the first, and the R2 and a C2, that's the second one. You also see here the unity-gain feedback configuration using this op-amp, and that's why we have a unity-gain in this configuration. Now when you look at a Bode plot for a specific low-pass filter, you see you have the passband and the stopband region, and here we designate our cutoff frequency, which is 3 dB lower than our low frequency gain. In this case, the low frequency gain is 1 because it's unity. That means in the dBs 0 dB, and this is the magnitude of our transfer function. Now for this circuit, the transfer function is given by this expression, so the Hs, which is in the Laplace domain, is given by the output voltage divided by the input voltage as shown here in the circuit, and that is given by this expression. You see here the S squared, which is then designated that this is a second order filter. You see here the 1 over the product of all the components here in this circuit. The same expression here, you see also that in the denominator. You see also the term with the S, where you see the product of the R1 and the C1 and the R2 and the C1. So we can use this, and this is the generic expression for the transfer function, but the most convenient way is to set the resistors and the capacitors equal to each other, so we can define as resistor, all of the resistors are the same and all the capacitors are the same, and then we have a more easy expression like so. We have then R squared and C squared since the capacitors and the resistors are exact same, and you also have here 1 over RC plus 1 over RC, it means 2 over RC. And you have here exact same as in the numerator. Okay, now we can of course make this more clear by multiplying the numerator and denominator by R squared C squared, and then you have this expression in the Laplace domain. Now we can go to the steady state analysis by defining or setting our S is equal to J omega. That is mostly done in the filter design. Then you have this expression. You see here the 1, and this part S squared is J omega in the quantity squared. That means then J omega times J omega. Now since J times J is minus 1, that's why you have this here minus omega squared. Now this is just a pure real part, so we can place this in the front. So that's what happens here, and then 1 minus this omega squared R squared C squared is the pure real part of the denominator of this transfer function, now given in the J omega domain instead of the S domain. And this part is the pure real part where you see here the 2 J omega RC, which is actually shown here. Now we can also go to the high pass filter configuration where you see now the circuit in the same configuration, only the resistors and the capacitors now has changed location. So this resistor R1 is now switch that way, and the capacitor is going that way, and actually see the same action here. So we have now two RC high pass configurations. Again, we have also the Unity-Gain feedback configuration for our operational amplifier. And this is now the generic Bode plot of a high pass filter. Again, you see the stop band and the pass band gain, or the high frequency gain, is 0 dB, since we have a unity gain, or the gain is 1. And this is now the absolute value of our transfer function expressed in dBs. Now for this case, the transfer function is similar to what we have for the low pass filter. The only change is here the s squared, and then you have here the expression again like the denominator here, but this is a little bit different. We have also here this R2 here and also R2 there, but C1 and C2 will actually change here, so it is almost the same, but not 100% exact the same. And then if we now set R is equal to R1 is equal to R2, and the C we define it as C1 and a C2, then we can express this like so, and we can have the following expression, that we have the numerator and the denominator multiplied by the R and C. And then you have this expression, and then again you're going to the steady state analysis by setting J omega, so S is J omega. Then you have this expression, which is a similar process as we have done for the low pass filter 2-pole. Okay, now getting all this here together, let's now look at the very important parameter, which is the cutoff frequency. This is defined as the low frequency gain over the square root of 2. So that is what we need to determine. Since for this circuit the low frequency gain is 1, so we can say it is 1 over the square root of 2. Now when you know what the transfer function is, which is actually shown here, you need to first determine the magnitude of your transfer function, and that's given here. So 1 over the square root of the real part squared plus the imaginary part squared. Of course you don't take the j, that is just an operator, and that is actually shown here. Now we need to use this expression and equate that to 1 over the square root of 2. Now since this is 1 and that is 1 for the numerators, left and right hand side, so that means the denominators must be equal to each other. Now we can also square the left and the right hand side, that's what we have here. And we can also work out the parentheses here. That's actually what we've done here. So first, this is easy, of course, 2 times 2 squared, and then omega squared r squared c squared. That's actually shown here. And this one is you work out the parentheses actually, then you get these 3 terms. Now we can now collect the terms also, because these 2 are exact same, only just here plus 1, plus 4 I mean, and minus 2. You can also move this 2 to the left side, and you have this reduced expression. Now we can solve this such that we find the omega which make this true. So we can set, in this case, since this is a 4th order expression, we can say let's define or set x is equal to omega squared. Then we have this simple expression which is now a quadratic expression. So we can solve this by the formulas we know. Like let's say we have an expression like ax squared plus bx plus c is 0. We know this from math courses. We can solve this, so we can find the solutions for x by using this generic formula. So we find the b, we find the a, we find the c, and we just use this formula, and we have now 2 solutions. Now solving, we get then the following situation. We know what the b is, we know what the a is, we know what the c is here, because this is the a, which is now actually shown here. This is the b, so 2 times r squared c squared, which is shown here because of the minus sign here. We just put the minus sign. We also know what the c is, which is actually just this minus 1. So that means since we need to do here minus 4 ac, we have then plus 4, and then a is here, which is actually from here, and then c is of course minus 1. Now all together here, we can also see that this is again 4 r to the power 4 and a c to the power 4. And then you have this situation, since this is also the same as that one, you get now 8 r to the power 4, c to the power 4. Now we can take out this r to the power 4 and c to the power 4 out of this square root, and then you have this situation, and then you only have the square root of 8 in your square root. Now we can now divide by the r squared c squared, the numerator and denominator. That's now actually what you see here. Now you see an expression where you have the solutions for x. So x is now equal to minus 1 plus or minus the square root of 2 over the r squared and c squared. The only solution which is valid is the one which has the positive part here. Why? Because if this was a negative, so if you have a solution which is a negative value for x, then this is impossible to fulfill because the omega squared cannot be made negative. So if you square the omega, that will be always positive. So it means your x will be also positive. So the solution with -1 minus the square root of 2 over this r squared c squared is not valid, which is then only valid solution is this one, and this part is positive. Now again, we know that the omega is then the square root of the x, and that means they will take the square root of this part, which is actually shown here. Now we take down the square root of the numerator and the denominator, and then you have a more simple expression. Now this is now the expression we can use, and this is also the definition for the omega c, which is, as we call it, the cutoff frequency in radians per second. Now, if you go to the hertz, you can just divide by the 2 pi, and then you have this expression. Now, very important note here, and let's bring all the expressions here for the high pass and low pass two-pole configurations. This was a transfer function for the low pass, and this was a transfer function for the high pass. And the cutoff frequency, or the -3 dB point, again in the radians per second and in the hertz, is this one. But I see sometimes in books and also on several websites or documents that the cutoff frequency is given by this expression, just like 1 over 2 pi RC, which is absolutely wrong. Because we see here that it's not 1, this is different. So we don't use that. So remember, don't just use or stick to 1 over 2 pi RC. This is only valid for simple RC circuits, so just first order, or if you have a very special configuration like the Bode response. But that is a special case, which is not always the case. So it depends on the filter configuration. Similar situation also is valid for the cutoff frequency for the high pass filter. Then the derivation is really similar. The only change what you make for the cutoff frequency omega is that you take this scaling, which is the square root of the -1 plus the square root of 2. You don't put it in the numerator, but in the denominator. And of course, for the cutoff frequency in hertz, the similar process, but you just divide by 2 pi. And again, don't use this formula, please. This is really wrong, and it's just a special case for first order low pass filters or special cases like the Bode response. So this is again a warning. Okay, now let's go to the Sallen-Key two-pole filter circuits. Now in this case, non-unity-gain. Okay, so we have again our low pass filters and the high pass filter, but in this case we use a gain. Now you see the similar configuration as we have discussed before. Now there was just a simple wire here. Now we have the R3 and R4 here, which makes that gain. So it is also actually looking from this node to output. This is actually a non-inverting amplifier. So transfer function here is a little bit different. It is similar, but you see here in the numerator 1 plus the R4 over R3, which is the gain of a non-inverting amplifier. We still have this 1 over R1, R2, C1 and C2. That's also the same here in the numerator. This has changed a little bit because of this R4 and R3. This is also the same as before for our low pass filter unity gain. Now, if we again make the simplification by making these two resistors exact same and these two capacitors exact same, just define it as R and C, then we have a more simple expression as shown here. And again, we can simplify that by multiplying the numerator and denominator by R squared C squared, and you have this expression. Again, we use the steady state analysis, so we just set S is equal to J omega, and then you have this expression. Again, this is our transfer function, which is a very important part we use to determine the cutoff frequencies and other necessary information. Now for the high pass filter, we have a similar configuration as we have done it for the unity gain. We'll see here again the R4 and R3 for our gain stage, as we have it here for the low pass. And we have also again 2 capacitors and 2 resistors. The transfer function is similar as we have it before. The only change is again because of this R4 and R3 here. That's why we have it here as the gain. And this part for the S, we also have this R4 and R3 here. The S squared has not changed, and also this 1 over the product of these 4 components is the same as before. Now if we set again our resistors and the capacitors, so these 2 capacitors and these 2 resistors equal to each other, Then we have a more simple expression that's actually shown here. And we can also write it down in this format so we see it clearly what happens. And again, if we go to the S is equal to j omega, which is our steady state analysis, then we have our transfer function for the high pass filter configuration 2-pole Sallen-Key with the gain. Okay, now let's now go to the cutoff frequency analysis for the low pass filter for this circuit. Now we will see again that we look at the situation of the low frequency gain divided by the square root of 2. Now the low frequency gain here in this case is not 1 but R4 over R3 plus 1. That is the non-inverting amplifier gain. And that one we will divide by the square root of 2. Now this was the expression for the transfer function. We know that, that's also shown here, but now we get the magnitude. And now we need to equate this expression to the expression here on the right side. That is actually shown here. Now we see clearly that the numerators are equal to each other, so we can divide it out. And which means actually that you have the denominator is equal to the denominator here. And that's shown here. Again, we can do the similar process. Square the left side and the right hand side of the equation, so we get a 2 here, and only the inside of this square root, and then you have this expression. Now what you see is you square actually this, you square also this quantity total and also the r squared and c squared, that's actually shown here. You also need to work out the parentheses here, so that's actually what we do next. So this goes here, you see again from here you get here now 3 terms. And also this is going to be worked out here, this part. So this is again worked out here. And that's still equal to 2. We can keep going and then work it out. That's actually shown here. Just make this 2 to the left side and you have here -1. That's actually shown here. And you can even go further. You can see also this r squared, c squared, omega squared. That's actually shown also here. But you also have here the -2, which is then making this for a +2, so actually you go down by 2. Now this is now the most simple expression you can make from here, and again we can try to analyze this by setting some parameters. In this case I will designate this as lambda. So lambda is in our case is 2 minus 4 times r4 over r3 plus r4 over r3 the quantity squared. And then I have now this expression, which is then r to the power 4, c to the power 4, omega to the power 4, choose this one, and then omega squared, r squared, c squared, lambda, which is just this one, -1, is equal to 0. We can now again set, for example, x is equal to omega squared, and then we can write the expression like so, and this is now a quadratic expression, or an equation we can solve using the formulas we know as this. So this is general form, a squared plus bx, ax squared I mean, plus bx plus c is 0. And these are the solutions using the a, b and the c's from this expression. You only need to look at the expression which you have here and then compare that with this expression and then solve for x. Now solving for x, we know again as we have done it before. This is the b of course, this is the a here in front, and this is the -1 which is the c. Now when you substitute here using this formula, you get this expression. Again, we can continue by taking out this r to the power 4 and a c to the power 4, which you also have here. Take it out, then you have only here the lambda squared plus 4, which is actually shown here. Again, divide by the r squared, c squared, the numerator and denominator, and that's actually shown here. And then we have an expression that you can use in order to go to the omega. Because this is the expression which is, or the solution which is only valid. Again, why? Because the omega squared needs to produce a positive value. So that is actually what is valid. If you make this also minus, so minus lambda minus the square root of the lambda squared plus 4, then you get an expression which has a negative value for x, which is of course not possible because the omega squared must be positive. Now we go down to the omega, which is the square root of x. That means square root of this one. So you take the square root of that one, that's actually shown here. And now you have the expression for the cutoff frequency, finally, as we wanted here. You can also go to the frequency in hertz. So you divide this expression which you have by 2 pi, and then you have the expression here, which is what you see is which is closely related to this, the most familiar 1 over the 2 pi RC for, expression for the cutoff frequency. but we have of course more, like this lambdas and there's numbers, etc. So you need to do more, which is not that simple, like 1 over 2 pi RC. Okay, now taking this again here together, and for the high pass filter we can also do the similar thing, but I will just give it in summary what we have now. This is what we have determined. Again, lambda was defined as this, and this is now the frequency, cutoff frequency in hertz. Now for the cutoff frequency of the high pass filter configuration for this circuit, you can go to the similar analysis, but it will be just flipping this scaling here, what you have here. You just need to flip, which is actually shown here. So you have the square root of 2 divided by now this square root with the lambdas. And then if you go now to the, again, lambda is exact same as before, but now if you go to the cutoff frequency in hertz, just divide this by 2 pi and you have this expression. Okay, now we have the necessary information for the 2-pole unity gain and 2-pole non-unity gain filters for the Sallen-Key configurations. Let's now go to the 3-pole, which has now 3 RC configurations. So we have a third order filter. In this case, we start again with the unity gain configuration. Okay, we start again now with a low pass filter analysis. This is the 3-pole Sallen-Key low pass filter, where you have again a unity gain feedback. You see here the RC, RC and RC, so 3 times low pass RC configuration. The transfer function, again, the analysis is quite lengthy and tedious, so I will give you the result. You see here again the product of all these components in the numerator. You see also that in the final form in the denominator or final term. But you also see here the s to the power 3, so s cubed, a part which is s squared, and also another part which is just s. Of course, derivation of this will be time consuming. I just give the result, but if you again make this simplification by setting the R1 is equal to R2 is equal to R3 and define it as R, and similarly for the C1, C2 and C3 and define it as C, then you have this very simple expression. Again, 1 over the R cubed and C cubed, and that can be then again written like this by multiplying the numerator and denominator by R to the power 3 and C to the power 3. Again, we need to go to the steady state analysis, so S is equal to J omega, and then you have this expression. Again, the similar analysis we have done it before. By looking at the S to the power 3 means that you do J omega times J omega times J omega, which is effectively minus J omega to the power 3. In a similar case also the other S squared, etc. And if you now collect the real parts and the imaginary parts in a nice form, then you have from this expression this nice final form of our transfer function for this low pass filter. Okay, now looking now at the high pass filter, a similar configuration, again the unity gain feedback. Now the capacitors are here and the resistors there, and now we look at the transfer function. It's almost the same as the high pass filter, I mean the low pass filter. The only change is here again this s cubed. Also the terms here for the s squared and also the s are a little bit different. This is the exact same as for the low pass filter, and this is also the same as for the low pass filter. But we can again make the same analysis by equating the resistors and the capacitors to each other. Then you have this expression, and again work out this more easily by multiplying the numerator and denominator by the r cubed and c cubed, and then you have this expression. Again, we go to the steady state analysis by doing s is equal to j omega, and then you have this expression, and written this in a more easy readable way where you have the real part and the imaginary part. Then this is the final part I will use as a transfer function. Okay, now the low pass filter transfer function is shown here. The cutoff frequency for this situation is again the similar analysis as we have done it before. The low frequency gain here is again 1, because this is unity gain feedback, and we divide that by square root of 2, and we need to take now the absolute value of this one and equate that to 1 over the square root of 2. So we take this, and that's actually shown here, and equal to 1 over the square root of 2. Again, denominator is equal to the square root of 2, that's shown here. Square the left side and the right hand side. Work out the parentheses, that's actually all shown here in detail. So 1 times 1, 1 times this minus 4r squared c squared omega squared. And again, of course, that's why we have it here minus 8. And then you also do minus 4r squared c squared omega squared times itself. Then you get here plus 16 r to the power 4 c to the power 4 omega to the power 4. You also need to work out, of course, these, and then you have a more simple expression like so, and then you can again solve this. Now, you can look at it in an also a little bit different way, because you see here the r, c, and omega in the parentheses to the power 6. The same here, but then to the power 4, and the same here and then to the power 2. So we can now equate that or set it as x. So we can say x is equal to r, c, omega. Then you have this expression, which is a sixth order expression or equation. Now we cannot solve this by hand, so we need to really use a solver for this. So for solving, and then you get an approximate answer, which is then saying x is approximately, very accurate actually here, 0.335004726. Of course, more numbers are here, but this is the very close value. I will use 0.335 as the x value. Of course, again, approximate. So then we have the following. Since x is equal to r, c, omega, omega is then equal to x over rc, and x is equal to this value, which is 0.335, we can say our cutoff frequency is also defined as this value, which is then 0.335 over this 2 pi rc as a unit of hertz. So we have our cutoff frequency. Again, we see this familiar 1 over 2 pi rc, but again we get a kind of a scaling, which is now in this case 0.335. That can only be determined when you do the analysis like so. You cannot just look at the circuit and you can say, oh, that's of course 0.335. So you need to do that really step by step carefully. Okay, now we again collect the circuit here, left side and right hand side. So left side low pass, right side high pass, transfer functions, and we see here again the cutoff frequency or the minus 3 dB point, which is determined, and also in hertz. Similar situation for the high pass is again this reverse configuration, so 1 over the 0.335 RC, and for the situation for in terms of hertz, so as a unit hertz, you actually divide by 2 pi. Okay, now we go to the Sallen-Key 3-pole filter circuits, but then unity-gain configuration. Now this is the most expanded configuration of the Sallen-Key filter. So you see here now 3 poles and also the gain stage. So we have also now the R4 and R5 as 2 resistors added here. Now the transfer function for this circuit is quite, again, tedious to work out. So I will just give you the result right away so we can use it later if necessary. You see here the K, and K is here defined as 1 plus the R5 over R4, which is the gain of a non-inverting amplifier looking from this node to that node. You see also the K appearing here, appearing there, and also there. So this is quite complicated. Again, we can make the simplification by making all the capacitors here, C1, C2, C2, C3 equal to each other, and also the resistors there. That can be done. So let's do that. And that's now shown here. So you see that this is much easier to read than this expression. And again, we can simplify this like so, and then going to the S is equal to J omega, then we go to the transfer function as we have it also for the other cases. Okay, now for the high pass filter, we have again a similar situation, and then we have the transfer function, which is then given like so. Again, we see here right away, I just start right away with equating this R1 is equal to R2 is equal to R3, and also the capacitors, and then you have this easy expression, and then we can again set S is equal to J omega, because we want to go to the steady state analysis, and then you have this one, or in the final form, this one. Again, the K is here equal to 1 plus R5 over R4. That's shown here. Okay, now look at the situation of the cutoff frequency for this situation. How does it work? Now, the cutoff frequency is again looking at the low frequency gain divided by the square root of 2. We start with a low pass filter. The low frequency gain is K, which is actually given by 1 plus R4 or R5 over R4. But do we know that? Not yet. But we can also use this transfer function for this low pass 3-pole circuit, and then equate this to this K over the square root of 2. That's what we do here. Now again, we lose the K from the left and right hand side, and then we need to do this square root is equal to the square root of 2. Again, you can square the left and right hand side. That's actually shown here. And again, work out the parentheses in detail, but that is quite lengthy, and this is also not simple to calculate, and we don't also have a very simple formula. So what we need to do here is a different way. We approach it in a different way. We can say for specific values of k, I just picked here some values just to see what happens. You can calculate or express the cutoff frequency. And if you change your value of k, you can have a different formula for your cutoff frequency. In this case, I start with k is 1. If k is 1, that means actually this R5 over R4 must be 0. That can only be the case if this R5 is 0, which is unity-gain feedback configuration as we have had that before. And then you get again this 0.335, that scaling we have seen before. So we see that here 1, if the k is 1, then you have this expression for the cutoff frequency, or of course this if you do it in hertz. Now if you go to 2, then you have your scaling, which is then like so. And if you go now to 5, then your scaling will be like so. And if you go now to 10, your scaling will be like so. And if you go to 20, so the k is 20, that means R5 over R4 will be 19. Then you have this one. So you actually see that this is changing and actually decreasing. It is of course increasing there, and then decreases, keep decreasing if you increase the gain. And say of course the same situation you also have for the cutoff frequency FC. Okay, what happens then for the high pass filter? That's similar problem we have also here. So we can again do the cutoff frequency, looking at the high frequency gain, which is k, and again we take the absolute value of this one, which is the magnitude, equate that to that one, try to solve it, which is of course impossible, again, because there is no simple formula for the cutoff frequency. Again, we set up the table and look at the situation, and we see actually here the results. Similar to what we have for the low pass filter, only changes the scalings here are now not in the numerator, but in the denominator. That's actually shown here. So again, I start with the k is 1, 2, 5, 10, 20, and 50. It's just some random values. You can also, of course, look at different values like 6 or 25 if you want, but this is just what I have done. What I did actually to get these expressions is just ask my solver, so can you solve this for me, of course for omega, and then I got actually this expression and then made these values for this table. Okay, let's now go to the part 2, which is the worked out examples for our Sallen-Key filter circuits. The first example about the Sallen-Key 2-pole low-pass filter with unity-gain. This is actually shown here. And we will use here the resistors R1 and R2 all 1 kilo ohm, and C1 and C2 will be 100 nanofarads. We like to calculate the cutoff frequency and also the low frequency gain for this circuit. Now we know that the transfer function is, we have determined that, so we have discussed that, that's actually shown here. And we know that the cutoff frequency for this situation is given by this expression. Now if I want to know the cutoff frequency, I just use the resistor and the capacitor value here, and that's shown here, and that will give me almost 1 kilohertz, so 1024 hertz. The low frequency gain is here given by the value for the magnitude of this one, where you substitute the omega is 0. That will result in 1 or 0 dBs. That's the result for the calculation. Now bring all these results here. Now look at the simulation results. This is another circuit in Nonunity-Gain SPICE simulator. You see here the input, the resistor R1 and R2, capacitor C1 and C2, the ideal op-amp in the unity-gain feedback configuration. And I have here now Bode plot here, which is showing in blue the gain. This is the gain, this is the frequency. What you see here first is that the slope is here minus 40 dB per decade. If you look at, for example, at 20 kilohertz, I have a gain of minus 44 dB. If you look at 10 times larger frequency, which is then 1 decade above, which is then 200 kilohertz, I go actually to minus 84 dB, which is then 40 dB down. That means we have a slope of minus 40 dB per decade, which is the characteristic of a second order filter, because for each order in the low pass you lose or you have a slope of minus 20 dB per decade. Now the cutoff frequency is shown here, which is then 1024 hertz as we have calculated. The low frequency gain is indeed 0 dB, so we have checked our calculations. Now, second example about the two-pole, but now this is now the high-pass filter, which is shown here. Again, the same capacitor and the resistor values, we also keep it the same. R1 is equal to R2, C1 is equal to C2. Again, the transfer function, just to remember what we have discussed. And the cutoff frequency here is, of course, similar to what we have for the low-pass filter. The only change is that the scaling is now in the denominator. Now we have again the resistors and the capacitor value. 10 to the power minus 7 is, of course, 100 nanofarads. And if you now substitute here the values, you get here almost 2.47 kilohertz or 2473 hertz. Now the high frequency gain is the gain where you have the situation where you have a high frequencies. For example, if you have very high frequencies, the capacitor will be here short, so it means you have actually a gain of unity, which is 1 or 0 dB. Now, collecting all the results here, looking at the simulations, you see here again the circuit in Nonunity-Ti SPICE, and I start first with the slope here, which is in this case plus 40 dB per decade, which is increasing, which is a high pass characteristics. You see at 10 Hertz, which is minus 88.1 dB, and if I go 10 times larger in frequency, 100 Hertz, I have here minus 48.1 dB. So I go up by 40 dB if I increase my frequency 10 times, which means 40 dB per decade. Now, looking at the cutoff frequency, you see here clearly, which is 2473 Hertz, as we have calculated, and also the high frequency gain is 0 dB. So this is also checked. Now, let's now go to the third example. Example number 3, we look at a 3-pole low-pass filter using, again, unity-gain configuration. That's actually shown here. Now we have here the R1 is equal to R2 is equal to R3, all of them 1 kilo, and all the capacitors are 100 nanofarads. Again, we like to calculate the cutoff frequency, in this case, the low frequency gain. So how to do that in the calculations? Now, first, just bring up the transfer function for completeness. Our cutoff frequency formula, we have discussed that it was approximately 0.335 over 2 pi RC. We know what our RC is because the R and the C's are given. We just substitute the values here and we have almost this 533 Hertz. The low frequency gain here is also 1, so that means it is 0 dB. Now bringing the results here, let's now look at the simulation results. You see here again the circuit in Nonunity-Ti SPICE. This is the Bode plot, and you also see here the slope, which is approximately minus 60 dB per decade. Why minus 60 dB per decade? Because we have now a third order. For each order, again, you get minus 20 dB per decade in the low pass, so you get now 3 times minus 20 dB. That means minus 60 dB per decade. You see here 10 kilohertz. It is minus 48.7 dB, and if I now increase the frequency 10 times, I go to minus 108 dB approximately, so which is, I go almost down by 60 dB. You can say, why is it not exact? Because I'm still in the vicinity of this cutoff frequency. If I look at higher frequencies, I have a much closer slope of minus 60 dB per decade. In addition, we see the cutoff frequency, which is close to what we have calculated, very close, so it is now 533.14. I also see here the low frequency gain, which is 0 dB, so it is exactly as we have it. So this is also checked. Okay, so let's go now to the example number 4, the Sallen-Key, now in this case, high-pass filter, 3-pole. Again, unity-gain feedback configuration. I have the same resistors and the same capacitor as before. I go again to the calculations and first look at the transfer function for completeness, and now look at the cutoff frequency. We know that we have now the scaling here in the denominator for the high pass. Substitute the values and we have now here 4751 Hertz. And high frequency gain here is also 1, so it's again 0 dB. Now taking the values here, let's now look at the simulation results. Again, our circuit in SPICE and our Bode plot for the gain in the blue. And you see here again the slope at 10 Hertz. I have here minus 132.1 dB. And at 100 Hertz, I have minus 72.2 dB. And the slope here is then approximately, looking at these two values, plus 60 dB per decade, which is a plus because we have a high pass filter here. And it is plus 60 because it is a third order, so you do 3 times 20 dB per decade. Now the cutoff frequency is also shown here, which is then 4751 Hertz, as we have calculated, thus checked. And also the high frequency gain is here 0 dB. Okay, that's all verified. Let's now go to the next example, example number 5, where we have now the two-pole low-pass filter again, but now we have non-unity-gain. You see the circuit here as before. Now we have this R4 and R3, which makes now the gain larger than 1. Again, we need to calculate the cutoff frequency and our low frequency gain. So we start with the calculations, and again we bring up our transfer function. Low frequency gain is then given by 1 plus the R4 over R3, which is also shown here actually from the transfer function by just substituting here omega 0. And then you have 1 plus 9000 over 1000, which is actually shown here. And then you get here 1 plus 9 is 10. In dBs, that is 20 log of this value, which is then 20 log of 10, which is then 20 dB exactly. Okay, now the cutoff frequency. We have discussed the cutoff frequency in great detail. The expression we have found was this, where we have the lambda, which is then given by this expression. Now, we know the R4 and we know the R3, so we can just calculate that using the values, and then it will be then 47. Now, substitute that in here, and also the resistors R and the capacitors C we have given here, and that will be then here in this case 232.1 Hertz. Okay, let's bring the values here, the results, and then look at the simulation results. This is now the Bode plot again. This is the circuit in SPICE simulator. You see here the R1, R2, C1, C2, R4 and R3, the ideal op-amp, and we see here the magnitude in the Bode plot. What we see is again our slope, which is there minus 40 dB per decade. In this case, by the way, not in the first part, because in this first part it's approximately minus 20 dB, and then later on it is steeper. If I look at the 50 kilohertz, I will have approximately minus 40 dB or minus 40.1 dB. If I now go to the 500 kilohertz, so 10 times larger in frequency, I almost go to minus 80 dB. So this is a decrease of almost 40 dB. That's why we have it minus 40 dB per decade. The cutoff frequency is here given by 232.1 Hertz, as we have it. This is, by the way, at this dB. Why? Because a low frequency gain is 10 or 20 dB. That's also what we have calculated. So you need to go down from the low frequency gain by 3 dB, or a little bit carefully 3.01 dB. Then you have this frequency that's also verified. Okay. Let's now go to the final example about the Sallen-Key two-pole high-pass filter, non-unity-gain, and now calculate also here the cutoff frequency and the high frequency gain. We have the same values for the resistors and the capacitors, and also the R4 and R3 are the same. Now, first the transfer function as we have it before, that's actually shown here, and the high frequency gain is also easily calculated just looking at the 1 plus the R4 over R3, in this case it's 10. And if you want to express it in dBs, then you have this expression, then you have again 20 dB. The cutoff frequency is similar to what we have seen for the low-pass filter, only changes that you flip the scaling here, and then you have here using the lambda, which is the exact same as before, it's 47, because we have the exact same component as before. And then you have this expression, just substitute here the 47, and you get now here almost 10.9 kilohertz. Okay. Let's now bring the results here. Also bring up the Bode plot. You see here the circuit in the T90i SPICE simulator. The Bode plot you see in blue here the gain. What we see is first the slope is approximately 40 dB per decade for this part of the graph. At 10 Hz it is minus 68.1 dB, and at 100 Hz, so 10 times larger in frequency, it is approximately minus 28 dB. So this is approximately 40 dB up. It's not exactly. Why? Because we are here close to the cutoff frequency. If I now go to the smaller frequencies, this slope is close to 40 dB. Now, the next one is about the cutoff frequency. You see indeed that is 10.914 kilohertz as we have calculated, so that's checked. And our high frequency gain is indeed 20 dB, which is then in scalar 10. So that's also verified. Alright, this was then our final example, concluding this lengthy video about the Sallen-Key filter configurations and many examples to illustrate the concept. I hope this clarifies the situation, and hope that you get a better understanding how you can use a transfer function to determine the cutoff frequency, and that the cutoff frequency is not always 1 over 2 pi R's we see most of the time for simple circuits. If you have any questions, comments, please let me know in the comment section. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.